Hello all, Finite Element Analysis lecture number 3. In this lecture we will continue from the lecture 2 where we had studied up to 3 steps in the analysis section. So we will go to the steps in finite element analysis. There are 10 steps in the general category: pre-processing, analysis and post-processing. We have seen in the previous lecture discretization, numbering of loads and elements, selection of displacement function or interpolation function. In this lecture, we will be studying the other steps from step 4 to step 10. So, we will go to the step 4. Step 4 is define the material behavior by using strain displacement and stress strain relationships. That is the step 4. Strain displacement and stress strain relationships are necessary for deriving the equations for each finite element. In case of one-dimensional deformation, the strain displacement relationship is given by E is equal to du by dx, where u is the displacement field variable along x direction and E is strain. That means du is the change in length and dx is the original length. Change in length by original length is the strain E. From that E, that is strain, we will use the stress strain relationship sigma is equal to capital E into small e, where sigma is the stress in x direction. Since we are dealing with one-dimensional problems, stress in x direction is only considered. So capital E is modulus of elasticity of or Young's modulus. So we will get the stress in x direction from this equation. Next is step 5. Derivation of element stiffness matrix and equations. The finite element equation in matrix form is given here. Left side is force vector in flower bracket, that is f1, f2, f3 up to fn, that is equal to, then there is a square matrix, its row numbers and column numbers will be equal, so it is a square matrix in square bracket, that is known as stiffness matrix, and that into another vector u1 up to un. So here in this equation, f and u are vectors and k is the stiffness matrix. So this is the finite element equation in matrix form. In compact form, we can write f is equal to k into u. F is the vector of nodal forces of elements, k is the element stiffness matrix, and u is the element displacement vector. F is equal to k into u. So here this form is for a particular element. In the equation F is equal to k into u, k is known as stiffness matrix. Some of the properties of stiffness matrix, or to become a stiffness matrix, the following things should be satisfied. Number 1 is it is a symmetric matrix. Number 2 is the sum of elements in any column must be equal to 0. Symmetric matrix means number of rows and columns are equal. So it is a square matrix. Then number 3 is it is an unstable element. So the determinant is equal to 0. So determinant of a stiffness matrix should be 0. Then number 4, the dimension of the global stiffness matrix K is capital N into N, where capital N is the number of nodes. This follows from the fact that each node has only 1 degree of freedom. Then number 5 is diagonal coefficients are always positive and relatively large when compared to the off diagonal values in the same row. So when we check a stiffness matrix, we can see that diagonal coefficients which are coming on the diagonal from top left hand to bottom right hand, the coefficients will be very large compared to off diagonal values. Now we will move to step 6. Step 6 is assemble the element equations to obtain the global or total equations. In step 5, we obtained individual element equations for each element. We know that after discretization we will have lot of elements in the body. So in each element we have got element equations like F is equal to K into U. Now in step 6 what we are going to do is we will combine all those equations, element equations together, and we will get a final assembled global equation which will be in the form F is equal to K into U, where K is the global force vector. In the previous case, for the element case, the vector F was element force vector, and here K is global stiffness matrix. The previous case for a particular element it was element stiffness matrix, and U is displacement vector, and it is known as global displacement vector after assembling all the element stiffness vectors. Step 7 is applying boundary conditions. Some boundary conditions should be applied in the finite element equation to get solution for U. U is the unknown we are going to find out. If in the current situation global stiffness matrix K is a singular matrix, because we already studied that its determinant is equal to 0. That should not happen. That should be removed. In order to remove this singularity problem, we are applying some boundary condition. Boundary conditions means uh, at the initial time or at the final time, what is the condition of a particular variable. For example, at time t equal to 0, velocity is 0 meter per second. That is a initial condition. That's a boundary condition. And at time 5 seconds, velocity v equal to 10 meter per second. That is another boundary condition. Like that, in the current finite element equation, we can give some boundary conditions like at time t equal to 0, f is equal to 0. F is coming on the left side of the equation, where we can put 0 if the initial condition is force equal to 0. By applying these boundary conditions, we can solve the equation. Wait, solution of unknown displacements. The set of simultaneous algebraic equations formed in step 6 can be solved, and unknown displacements U are calculated by using Gauss elimination method or Gauss-Seidel method. These methods we have studied in mathematics. Gauss elimination method or Gauss-Seidel method, that is a matrix solving method to find the unknown variables. In this case, we can use any of these methods to find the unknown variables. Here the unknown variable will be U. That is step 8. Then we will go to step 9. Computation of element strains and stress from the nodal displacements U. From step 8, we have already solved U. Solved for U, and we have the value of U. Then we can find out strain first using the equation E is equal to du by dx. This equation we have seen earlier, where du is displacement along x direction, that is u2 minus u1. u1 and u2 are the displacements at node 1 and node 2 respectively. Dx can be written as x2 minus x1, that is the actual length of the element. Change in length by original length. That formula is used here, E is equal to du by dx. So we have got the value for strain. Now from the strain value we can calculate stress. That is what we are going to calculate. Sigma is equal to capital E into small e, where capital E is Young's modulus. This equation also we have seen earlier. So stress in the element, stress in the material under study can be calculated in this way. Coming under the post processing, interpret the results. Analysis and evaluation of the solution results in referred to as post processing is referred to as post processing. Post processor computer programs help the user to interpret the results by displaying them in graphical form. We have seen this picture earlier, that is a deformation of a spur gear teeth. This teeth, this figure we will get in the post processing step. From this figure we can analyze the results, whether the deformation is within the limits prescribed, or this figure is for the deformation. Other figures like stress, strain, velocity, etc. can also be obtained in the final step, that is post processing step. So these are the steps of a finite element analysis, general steps in finite element analysis, and this is very important. You need to study it very well, and write each step and study each step thoroughly.